In the previous examples, the centre of gravity position and limits were given as distances from a datum. As an alternative, the position of the centre of gravity and its limits can be expressed as a percentage of something called the Mean Aerodynamic Chord, or MAC. This is the preferred method used on many swept-wing commercial aeroplanes, because the centre of gravity affects many aerodynamic characteristics, in particular stability. Before we proceed with examples, the definition of a chord and mean aerodynamic chord must be understood. The chord line is a straight line joining the leading and trailing edges of the wing. The mean aerodynamic chord is the length of the chord of a rectangular wing, with the same area and having the same aerodynamic characteristics as the original wing. We can now calculate the centre of gravity as the percentage of the mean aerodynamic chord. The length of the mean aerodynamic chord is constant and is a fixed distance from the datum. The first distance to use is the distance of the leading edge of the mean aerodynamic chord from the datum, indicated by the letter B. The second distance is the distance of the centre of gravity from the datum, which is indicated by the letter A. The length of the mean aerodynamic chord is allocated to the letter C. We now have the three parts, A, B and C, which make up the formula used to calculate centre of gravity in terms of percentage mean aerodynamic chord. The formula used to calculate percentage mean aerodynamic chord is A minus B divided by C multiplied by 100. Let us put the theory into practice and work through an example to calculate the mean aerodynamic chord, given values of A and B and C. The distance of the centre of gravity from datum A is 420 inches. The distance of the leading edge of the mean aerodynamic chord from the datum is 380 inches. The length of the mean aerodynamic chord C is 120 inches. Write down the formula for calculating the centre of gravity as mean aerodynamic chord. We can now enter the values of A, 420, the value of B, 380, and C, 120. Resolving the equation shows us that the centre of gravity as a percentage of mean aerodynamic chord is 33%. Here is another example using the same percentage aerodynamic chord formula, but this time we are required to find distance A. Notice that the aeroplane looks the same as our previous example, but the datum is changed. Remember, the datum is set by the manufacturer. The values given are B, which is minus 26 inches, C, which is 73 inches, and percentage mean aerodynamic chord is 21%. The distance of the centre of gravity from the datum A is the unknown value to be calculated. The values are input in the formula to find A, and when resolved, show that the centre of gravity is 10.67 inches forward of the datum. Notice that because B is forward of the datum, it is a minus, and therefore it is advisable to put it in brackets before applying the minus sign after A. We have looked at calculating the centre of gravity in relation to the aeroplane datum, and now as a percentage of the mean aerodynamic chord, both of which are used by aeroplane operators. It is important to remind ourselves that once the centre of gravity has been established, by whatever method, it must be checked against the certificated limits.